Hi, in this video, we want to take a look at the Poisson-Gamma model for modeling spatial real data. All right, so remember when we're talking about real data, we're talking about things like neighborhoods, counties, school districts, and states, countries, things like geographic regions that don't overlap. Now, what we're going to be doing here is we're going to be taking the conditional autoregressive format that we've looked at in a previous video, and now we're going to pull in covariates into our models to get a more complete representation of what's going on. This will also help eliminate confounding variables when we can pull them in, or a surrogate of the confounding variable. So we're going to run through examples from chapter 10 of Applied Spatial Data Analysis with R. This is in the disease mapping chapter. Here are the authors of the textbook. Here's the textbook's website, and you can download this for free, the PDF of the textbook for free through UCF's library. It's a Springer link document. All right, so now let's get down to Poisson-Gamma. Now, what we're going to be doing here is we're going to be taking a Bayesian approach. All right, so first thing I want to say, I want to talk about the Bayesian modeling structure, advantages and disadvantages. There's some powerful advantages and there's some powerful disadvantages when we choose this route. So we need to be mindful of what we're doing. Ultimately, when we build models, the goal is to convince somebody of something. And so I need to consider what is my audience ready to accept when I do my statistical modeling. If they're not ready to accept it, there's no point in me even building the model. All right, so here's some advantages of Bayesian statistics. All right, so really, they give a much more complete representation of what's happening. I mean, we get like way more in-depth insight into what's going on. And we get insight into the parameters, we get entire distributions instead of just point estimates. Okay. Now, also, our choice of priors gives additional flexibility in our modeling. Also, something that is a huge advantage, and this one is a big one, is that the structure of our prior distributions enables us to pull in subject matter experts so much more than we can with the frequentist point of view. So what we can do, I can talk to someone who knows the material very well. Maybe they don't know the math, maybe they don't know the statistics, but they know their subject well. They are an expert in what they're talking about. I get insights from them, and then I can convert what they say into a mathematical situation. And then I use that in my modeling as the prior distribution for before I start considering the observed data. Also, we get credible intervals instead of point estimates, usually is how we approach this. And so this is, once again, gives us a more complete view of what's going on when we evaluate something. Now, these advantages are huge, but they come at a cost. And we need to think about that when we do Bayesian statistics. First and foremost, this could take a long time to compute. I mean, this might be like hit the run button and go and come back in the morning. Honestly, I've had that at work. These are mathematically more complicated than the frequentist models. Also, I find this more with like older practitioners, is that you can get resistance from people in the field. I've seen that, academically, mainly academically, I've seen more resistance, but I've also seen that professionally. All right, so when we have additional choices, with great power comes great responsibility. If I have additional choices in my modeling, I have additional opportunities to make a mistake. That cannot be understated. So, it cannot be overstated. So if I'm going to create a situation where I have to make more choices, make more decisions, I have to be mindful of the fact that this is more opportunities for making a poor choice. This can bias our results. I can make choices that honestly, in the Bayesian statistics realm, I could make potential choices in what's happening so that our data really has no input on what's going on. Now that might be good, that might be bad, but if my data has very little input, then I'm biasing things in the direction of my prior. Something to be mindful of. Now, we get more complete presentation, but that doesn't mean we get to more informative value. We get some information that honestly we don't care about. All right, so a moment ago, I talked about the biasing effect of priors. And so what we can do, we can make choices that protect us from bias. But honestly, a lot of times when we protect ourselves from bias, we end up in actual applications getting results that are too vague to really give us an informative value that offsets the other disadvantages. So I have a more complete representation, but it's a vague representation that doesn't give me precise information. Also, and this is one I have had professionally to deal with, is that convergence can be a problem. Now, for me, my experience with this is that when you have small data, you have data with conflicting signals, or you have a poor combination of model structure and data, convergence will be an issue. And so if you have trouble getting it to converge, take that as a sign as you have a problem you need to deal with. All right, so if I'm using a distribution instead of a single point estimate, I need to make a decision on how am I going to use that distribution. So this is another choice. And someone else may make a different decision. Maybe I could use the mean or the median or the mode, credible intervals. We have more choices to make. Someone looking at the same thing might make a different decision. He uses mean, I use median. And if it's a skewed distribution, we might have differing opinions and we might have to just resolve this. Now here, this is one I've had experience professionally and when just studying things on my own, is that if you're using Monte Carlo Markov chains to build your models, which you will be using if you're not using conjugate priors, these can be computationally complex. So when I mean computationally complex, it might be like today it ran and tomorrow it doesn't, and you don't know what happened. The code changed. All you did was restart your machine, and now your code doesn't run. You could a buddy could hand you some code, you attempt to run it, it doesn't work. And that's in addition to not being repeatable. So this is something to watch out for. All right, so now, if you're going to use a Monte Carlo Markov chain model, even if it's Bayesian or not, it's absolutely critical that you check that it computationally converged. If it did not computationally converge, you have a garbage model, you cannot trust it. Here, I'm not going to check it in these examples, but be mindful of it, check the outputs. If it hasn't converged, don't trust it. Now, hierarchical models have our observed data depending on parameters, just like non-hierarchical models, but go one step further in saying that those parameters depend on other parameters and a distribution. All right, so we have data depends on a distribution with parameters. Those parameters depend on distributions with parameters. And potentially we can keep on doing this, chaining this even farther, and that's our hierarchical model structure. In non-hierarchical models, we say that our data depends on distribution and parameters, and that's it, done. All right, so this gives us flexibility in our modeling and enables us to limit our modeling to things that can be like written down mathematically. All right, so if I start working on some models, it's possible that I can get a distribution, but that distribution is very complicated if it's empirical, and I really don't have a clean presentation of what it is in terms of pencil and paper mathematics. In the Bayesian setup, it's possible to make sure that everything I have, even if it's hierarchical in nature with multiple levels, every individual step is mathematically clean in that I have a pencil and paper presentation of it. Now, while we do this, each layer of parameters accounts for a different source of variation. All right, so the BYM model, and that stands for the initials of the authors of the paper that initially proposed this, is a type of model that splits the variability into in a region as a sum of spatially correlated variables, which depends on the values of its neighbors, plus an area independent effect, which reflects the local heterogeneity. All right, so what do we have? We have psi, we have phi, and we have theta. These are random effects for each observation. And here, for the disease modeling, the theta will be our relative risk. Now, what's going to end up happening is that if you are working in the car base package, we're going to get psi as an output. We won't see phi or theta. So theta is our independent non-spatial random effects with zero mean and constant variance. And theta is our relative risk. Psi are autocorrelated spatial random effects with mean depending on neighbors and variance inversely proportional to variance weight. All right, so here that's just this long sentence goes longer than the width of my screen. That is just articulating that phi depends on its neighbors. So there's the neighbor aspect. Here we have a coefficient of proportionality for the variance, and we can see that here is the mean depends on neighbors, and then we have a weighted proportional, inverse proportional relationship to neighbor weights. Here, relative risk is normally distributed. And we are going to say that tau squared and sigma squared are inverse gamma. The direct estimates of the variables in the model can seldom be obtained by using Bayesian hierarchical models. Their posterior distributions can be attained by means of Monte Carlo Markov chain techniques. All right, so what we're going to do, we're going to use Bayesian statistics, and we're going to use Monte Carlo Markov chain techniques to get distributions of these parameters. And how MCMC works is by generating simulations of the parameters. And then we're going to take those simulations. So what's going to happen is that it's going to run a bunch of simulations. The first few thousand are going to be what we call burn-in. These are just to get things going, to get things close enough to convergence that we can start accepting the values. Because of the computational aspect of burn-in, of convergence, the burn-in part gets thrown away and we don't even consider it. After the burn-in phase of the simulations, we believe that our simulations have gotten close enough to the true distribution that we can keep them. Then we do a thinning step where maybe once every 10 simulations we take one. Why do we do the thinning? The thinning is to make sure that if I have if I do not have independence between consecutive values, that by thinning out that the dependence between consecutive observations will be thin enough that I don't have to worry about it. So once every 10th observation and once every 10th simulation, we accept it. We reject 9 out of the 10. Now, and that's after the burn-in. So if you think about it, we're taking less than 1/10 of our simulations in this. There's a lot of computational waste in here. Now, fortunately, it's a computer, it runs it, we don't care. But if time is an issue, this could be a problem for us. All right, so the Poisson-Gamma model can be regarded as modeling random effects in the log scale. So we have the log of relative risk. And this can be seen as a set of random effects with common prior distribution. All right, so how do we set this up? We're going to say that our actual observed counts are Poisson random variables of the expected value times the relative risk. Log of relative risk is equal to an intercept plus non-spatial random effect. So the I indicates the region that we're interested in. Remember, we're talking about a real data. We're talking about something like neighbors or counties or states, countries, something like that. So alpha is the intercept or the overall risk of the study region. And it's normally distributed, mean zero, and we have a constant variance for across the entire region. And we only have one intercept. And now here, U sub I is the non-spatial random effects that accounts for the differences in the areas. All right, so now let's start doing some actual computations. Let's execute this and get this going. All right, so now let's go ahead and append, to keep things organized in my data set, I'm going to append row numbers to my data set to use them as ID numbers. So the ID value is just going to be the row number for this purpose. As simple as possible. That way, if things get mixed up, I can always go back to where it was before. Now, let's go ahead and estimate a star model using Bayes X. Bayes X has 3 inferential components for estimation: the Monte Carlo Markov chain, estimation based on mixed model technology and restricted maximum likelihood, and the penalized least squares. All right, so here we're just working this out. What we're going to do, we're going to say that this is our observed value. Now we're going to have a smoothing function. This Bayes X function is similar to GAM, generalized additive model, in this aspect. That uses a smoothing function. And for the smoothing, we're going to just have the area ID. We're going to set an offset by the expected value. It's going to be a Poisson family. And here I'm just setting up what my data is. I'm extracting the data frame from the spatial polygons data frame. All right, so let's get the ratio of the fitted values to the expected value. So here I've got the fitted value and the expected value. Now, something you will notice is I go through and I resort this. So Bayes X does something that's kind of aggravating and frustrating, is that it permutes things around in a format to be more computationally consistent for itself. The problem with that is that by permuting it, I don't have that one-to-one correspondence I have anymore, like I do with most functions in R. So this I consider a major disadvantage, because if you forget about it, you can have problems, because you're just from your perspective, it can be randomly permuted the results. You need to manually go through and connect things back. All right, now let's go ahead and visualize what we've got going on. And so here we can just see what our fitted values are. All right, so now let's start looking at spatial models. All right, so what we're going to do, we're going to incorporate covariates into our model. All right, well, we're going to take a conditional autoregressive point of view on our covariates in addition to the conditional autoregressive point of view for our target variable. All right, so remember, when I say conditional autoregressive, what I'm saying is that a variable in a county or whatever type of region you have, but the variable of interest in our county has a regressive relationship, regression aspect with the neighboring counties. Okay, so here, what we're going to do, we're going to say that the Wij is the weight of the neighbor on the county of interest. And so here, I'm going to say that the variable of interest, I is the county that I'm interested in. J is the neighboring counties. So here, this says how much the neighbor of county I influences the outcome of this variable. And so what we're saying is that if it's going to be high, if the variable is going to be high in one county, it's probably going to be high in the neighboring counties also. And here we're taking a weighted average. And here we have a inverse proportional variance. And so you'll notice that the more counties involved, the lower my variance is going to be on this. And so, and we're representing V as a spatial effect. All right, so why do we do this? Why do we pull in the covariate? Well, what we want to do, we want to eliminate that variable as a confounding variable in what we see in our model. That's really why we do this. Now, what we're going to do, if we see that 0 is less than our lower bound of our 95% credible interval, we're going to conclude that there's a positive relationship between risk and the variable. Okay, so now what I'm saying here is credible interval, it's formulated different, and there is a different interpretation than confidence intervals, but operationally, honestly, take the point of view of this is like confidence interval, but I'm going from the distribution instead. And we generally treat it the same. There is a difference, but operationally, we treat it very similar to a confidence interval. All right, so now what we want to do, we want to consider the white, non-white aspects of the population in our SIDS data set. So in the videos, I've been talking about SIDS, very sad subject, very unfortunate. And what we want to do, we want to consider, racial, ethnic aspects in our modeling. So what we're going to do is we're going to pull in what data I have available. And so what we have is the proportion of whites and non-whites in births in each county. And so what we're going to do, we're going to use the fraction of non-white births as a covariate in our modeling as we work through this. All right, so here, let's go ahead and visualize it. So I have fraction of non-white births. Here is me just computing the fraction of non-white births. And I chose this coloring scheme. I figured if it's the fraction of non-whites, I put the whiter color as when there's more white and the blacker color for non-whites. Hopefully that makes it easier to interpret. So we can see that there were proportionally more non-white babies born in the darker regions. All right, now something that we're going to need to do to be able to work with the upcoming computations for our neighbors is that we're going to need a neighbor object that has the source of weights in the format the function can use. And what I'm going to do, I'm going to use a neighbor to graph format. So what this does, this takes the neighbor object that we already have established from the previous videos and converts it to a graph. This is our neighbor object here. And now we're going to use the Bayes X function to say that the observed number of SIDS depends on the fraction of non-white births plus a smoothing term on the counties like this. And here we're incorporating the neighbor aspect of the counties. We're going to include an offset of the expected value as a Poisson family. And here I'm just extracting the data frame. I don't need the spatial polygon data frame aspect because the graph is taking care of the neighbor aspect. All right, so now let's go ahead and fit a random effects conditional autoregressive model on the observed values depending on non-white births. All right, so here I'm just getting the data frame set up. I'm attaching it. In general, you don't want to use attach, detach, but the author chose to, so I went ahead and did it. And now what I'm going to do is I'm going to run the car-Bayes package implementation of conditional autoregressive with a BYM random effects model. And you'll notice that I've got observed SID status. So this is really the same model, but being computed in different ways. One thing that you will notice that mathematically, we could, in different packages, I could have mathematically the same thing, but when I run the actual implementation, the actual code with different packages, different functions, I could get different outputs. Here, they're going to end up being pretty close, which is usually the case, but you will notice a difference. So just be ready for that. So I'm saying that the number of SIDS depends on the fraction of non-white births plus an offset, saying what my data is, Poisson distribution, and here I'm getting my neighbor aspect. Now, you'll notice I'm putting this as a binary neighboring. Remember that anytime I'm doing spatial statistics, real data, if I make poor choices on my neighbors, I can wreck my modeling. So hopefully binary is the correct way to go. This is what the author chose. I ran with it. Now here's the number of samples. We're saying the first 20,000 are going to get thrown out. After I get past 20,000, every 10th observation will be kept. The reason why we thin it out to 1 out of 10 is that this will make this, the goal of this is to make sure that if there is a non-independent aspect between consecutive observations, hopefully 1 out of 10 is enough that I don't have to worry about that any further. And if I have the default verbose equals true, I'm going to get a bunch of crap printed out I don't care about. So now let's go ahead and print this up. And here we can see that, here we get the mean of our intercept, or mean of all the parameters, coefficient for fraction non-white births, estimate of variance. Remember, I've got two different variance aspects from inverse gamma. Here I get our credible intervals. You'll notice that 0 is not in there. 0 is not in there. 1 is not in here for the variances. All right, so now let's go ahead and extract the FID values. All right, so remember, whenever I'm using Bayes X, I have to address the fact that things get shuffled around in the computations. And then I divide by the expected value. And then for the conditional autoregressive BYM model, I just grab the FID values and I'm dividing by the expected value. So now let's go ahead and print it. And we can see that they're pretty close. Now, if I was to like start really digging in and go bit by bit, like this county is a little bit bluer up here for car-Bayes and Bayes X. We do see some difference, but overall, very consistent results. Right here, we have a changing color. All right, so now let's go ahead and visualize the intercept fixed effects, the posterior distribution. So we had a prior distribution, And now what I've done, I've taken the prior distribution in my observed data in the computations. I have a new updated distribution. The prior distribution that represents my belief before I observed data. I observe data, put them together, I get my posterior. This is now my best estimate of what's going on for the intercepts. All right, so here, the red is the Bayes X, and the blue is the car Bayes. Now let's look at the non-white coefficients, fixed effects, posterior. You can see the Bayes X is in the red, the car Bayes is in the blue. So I think we probably could have gone a little bit further to get convergence for car Bayes, but honestly, I would accept this for work. I would run with it. This is close enough to being unimodal that I wouldn't have a problem with it. Now let's look at the non-spatial random effects. All right, so Bayes X, this is the red is the non-spatial random effects. Unfortunately, with car Bayes, the spatial and non-spatial random effects are together in that summation. We get the psi, we don't get the phi and the theta. So they're added together. I look at this, I feel like this has not converged. I would be like, if I needed this, if I needed it for work, I would go ahead and increase the number of simulations before I would accept this for work, by the way. And now let's do the spatial random effects. So we had non-spatial and spatial random effects. Here's the Bayes X one. All right, this bump, I'm not really happy with that the red bump here. I usually would expect it to be unimodal completely. So maybe we want to rerun this with increased number of simulations. And then car Bayes, same opinion as before. Remember, I have spatial and non-spatial random effects added together here. All right, well, that's all I've got for you. Take care and goodbye.